Morning. ஓகே ஓகே மெயில் பண்ண சொல்லியிருக்கேங்க மேம். இந்த மெயில் ஐடி மட்டும் எனக்கு வந்து இதில் அனுப்புறீங்களா? நான் உங்களுக்கு நான் ஷேர் பண்ணேன். இப்போ இந்த மார்க்கெட் ஆட் பண்ணி கொள்ளாது. சரிங்க. ஓகே ஓகே ஓகே. There was nobody in the hotel there, so that's not a problem. Just that you can submit in the evening. But I can just leave it in the hotel, right? To the reception desk. Yes. Yeah, yeah. No, in the C form, right? On the bottom, there will be an email. Okay, for which you have to send the passport, visa, and okay, I don't have data, so it's I lost it. I just send the passport. So this for right, the same thing here. Okay. So, how thank you. Driver will call you. Yes. Before she was handed over to the driver. Which one? Yeah, yeah.
We started, yes, but it's more panels than or inverse. Was that not working much? But I had a problem, and I was if I have a singular or positive semi-definite matrix, if I demand that I want the rank of the generalized inverse should be the same as the original matrix, then it becomes a reflexive generalized. If I want that the column space should be the same, then I think you will get to more Penrose inverse.
Yeah, but not really, sir. Like you just want the column space to be same.
Yeah, but it's a positive semi-definite matrix. It's not the yes to symmetric.
Sean is there?
Yes, sir.
Can you bring him on? No, it is his session. Okay. You 9:15. So audio is on, so you can call. Okay. Yeah. Just I want to know whether he is there. He is available.
Good evening, Sean. How are you? I'm Prasad. Yeah,
Hi, how are you?
fine. We missed your physical presence, but still happy that you're available online.
Well, thank you for giving me this opportunity.
Okay, yeah. I was coming back running. So that's okay. Is it time for the session? Still, 1 more minute is there. That's what.
For sure.
So, how is the weather in Canada? Cold?
Cold, yeah, minus 5 right now. Yeah.
Yeah, it is quite warm here.
Oh, really?
Yeah, it is our pleasant weather.
Okay. Yeah, actually, it's been a mild winter here, not too bad.
Okay.
Yeah.
Please come. Raksha is there.
Good morning, everyone. Welcome back to the fourth and final day of our conference ICLA 2023.
Sure.
So without much further ado, let us start the session with a plenary talk from Professor Sean Fallat from University of Regina, Canada. I request Dr. S.K. Niyogi to chair this session. So please.
So first of all, I welcome you all in today's plenary session. Our plenary speaker is Professor Sean Fallat, and the title of the talk is Total Positivity, Entry-Wise Behaviors to Determinantal Inequalities. So about the speaker, all of you know Professor Fallat. Still that, let me narrate some details. Professor main research interests are in the areas of linear algebra, matrix theory, and combinatorics. Mainly on problems from combinatorial matrix theory, which of course overlap graph theory and linear algebra. He has been working on different problems which fall under positivity classes of matrices, algebraic graph theory, and commutative matrix theory. He has written a book titled Total in Non-Negative Matrices. He has supervised many PhD students, graduates, and undergraduates. As a professor, he is dedicated to serving both university community and the surrounding community at large. So over to you, Professor Fallat, for the talk.
Thank you very much for the kind introduction. Everyone can see the slides, I hope.
Yes.
Okay. So as pointed out, my talk today is on this question about total positivity. I'll speak to you a little bit about the entry-wise preservers side of things, even though that's not necessarily my pure expertise, but I will also get to determinantal inequalities along the way. So the outline of my talk today, I will mostly concentrate on the so-called entry-wise products of matrices, but I will talk a little bit more broadly about other kinds of products. I'll introduce and discuss positivity preservers, mostly in the context of totally positive matrices, and then I'll explain how that led me down a path towards looking at determinantal inequalities, and then I'll get to a conclusion at the end of the lecture. So I'll begin at the very beginning, just talking about this kind of sort of setting, the background setting. First, because I'm not sure how folks introduce these concepts throughout the conference, I'll just do this again here for you all so that it's straight in terms of my lecture. So there's a lot of different kinds of positivity, and with some regret, I'll explain lots of different kinds of positivity in my talk. Entry-wise non-negativity or entry-wise positivity is denoted in my lecture as A bigger than or equal to 0, and of course refers to the fact that the entries of a matrix are bigger than or equal to 0. Perhaps the most discussed notion of positivity in matrices is that when a matrix is positive semi-definite or positive definite, and that definition there is in front of you and is sort of well known. Perhaps less well known, but certainly still important, is the concept of a matrix being totally positive or totally non-negative. And here, that is when you require the determinant of every square submatrix of the matrix to be either positive or non-negative, depending on which situation you're in. Throughout my lecture, I'm going to require all the matrices to be square, but for many of these classes, it's not necessary that the matrices be square. Just to make matters, better or worse, you can talk about things called doubly non-negative, which is in some regard the overlap between entry-wise non-negative and positive semi-definite. And then there's even a concept of completely positive, just another adjective in front of positive, where it's a little stronger than being doubly non-negative. And I will come back to the concept of complete positivity later in the lecture. But I just wanted to mostly just set out the definitions and then, of course, the notation there on the slides so that we're all set for the different kinds of positivity that I'll get to. I had the pleasure of meeting Roger Horn in 1992, which, of course, will date me a little bit. He gave a lecture at the University of Victoria when I was a young undergraduate. And this was the title of his lecture, The Hadamard Product of Matrices, A Sophomore's Dream. And of course, for those of us that have taught linear algebra, we understand what Roger meant by this title in the sense that when folks first learn about how to multiply matrices, they probably wish that multiplication was defined entry-wise as opposed to how it typically is defined. And of course, the Hadamard product in this definition, I mostly want you to pay attention to the notation A circ B, meaning that this is how I define the entry-wise product of two matrices. It's also known as the Hadamard product, the Schur product, and there may be other names, but that's what I'm going to use throughout my talk. And perhaps one of the most important theorems regarding this product and the context of positive semi-definite matrices is that positive semi-definite matrices or positive definite matrices, they're closed under this product. And so that's handy. I mean, because positive definite matrices or positive semi-definite are not closed under the conventional product. I mean, they're the product is not arbitrary, but I mean, it need not be positive definite. So in the context of positive semi-definite matrices, for example, the Schur product, you have closure, and conventional product, you do not. Now, if I switch gears and I go to the other form of positivity that I wish to concentrate on, the total positivity or total non-negativity, then the situation completely changes. So totally positive matrices or totally non-negative matrices, however you wish, they are closed under conventional multiplication. So they do form a semi-group, and that's a consequence of the famous Cauchy-Binet identity for totally non-negative, or excuse me, for the determinant of a product. And then, of course, sadly, totally positive matrices or totally non-negative need not be closed under the Schur product. And here's just a simple example to show you that you can't do that. So on the positive definite side, you have closure under Schur product, but not conventional. And in the totally non-negative side, you have closure under the conventional product, but not the Schur product. Okay, so that's a distinguishing feature that I presume is interesting. Now, if folks haven't seen so much about totally positive matrices, then perhaps it seems like a bit of a strange concept that you require all the minors of a matrix to be positive. And indeed, that definition sort of lends itself to some curiosity. But it turns out that totally positive matrices arise in numerous areas in mathematics, not just in matrix theory. And for example, maybe one of the more famous matrices out there, the Vandermonde matrix that I presented here on the slide, it turns out that, I mean, most people who have studied, basic linear algebra know this determinantal identity associated with a square Vandermonde. But in fact, you can work harder to actually show that if if the X's you've picked here representing this matrix are ordered and positive, then in fact, the Vandermonde matrix is actually a totally positive matrix. It doesn't just have a positive determinant. In fact, the determinant of any submatrix, any square submatrix, is positive. And you only require this condition on the X's, that you be distinct and that they're ordered in this manner and that they be positive. And so there is an honest to God, totally positive matrix that you can, sort of get your hands on. And essentially the verification of that is not any more difficult than verifying this determinant formula for the Vandermonde matrix. Some other, if I can, some other topics associated with, properties associated with TN matrices. As I mentioned, they're closed under multiplication. They're not closed under inversion, although they're not that far off, but I'll just leave it as stated. If there is this nice, topological property, if you wish, that the totally positive matrices are dense in the set of TN matrices, just in the usual topology. Perhaps more interesting in this regard is on the eigenvalues of such matrices. Don't worry too much about this other symbol OSC. These are so-called oscillatory matrices. For the purposes of this lecture, the eigenvalues of a totally positive matrix are all real, they are all positive, and they are necessarily distinct. So that's a feature of positive definite matrices, right? The eigenvalues are real and positive, not necessarily distinct for that matter, but real and positive. And then because of the closure property above, you can conclude that the eigenvalues of TN matrices are, of course, stay real, but you may lose the positivity and the distinctness when you use continuity. Eigenvectors are also somewhat interesting. I don't have time, nor, that's not part of the lecture per se, but they have a very interesting structure, and you can look that up, or I can discuss it another time. Unlike positive semi-definite matrices, you cannot just permute rows and columns as you wish in a TN matrix, because of course, one of the basic determinantal properties you learn is that when you swap two rows, the determinant switches sign. So there's sort of no hope in doing that. And I'll just say that you can check if a matrix is totally positive in about n cubed time if the matrix has size n by n. So it's really easy for a machine to check if a matrix is actually totally positive. I mean, you in theory, you do not have to check the positivity of every single minor, because of course there's, it's well understood that there are all these kind of relationships among minors, and so you don't have to work that hard. But nonetheless, that is curious that you can do it rather quickly. Going back to the Vandermonde matrix, I just want to sort of show you this kind of factorization. So here's a Vandermonde matrix 3 by 3, but so I could fit it on the screen. And what I've done is I factored it into LDU, so the lower diagonal and upper. And then what I've done is I've taken that lower triangular matrix and the upper triangular matrix, and I further factored them into these so-called bidiagonal factors. And so they're just presented for you on the board. There's the lower triangular part, there's the diagonal matrix, and then here's the upper triangular part. And then what I've done below, just to sort of do this in sort of shorthand, is I've just written out this factorization. Please don't worry so much about what the symbols mean. It's just that they're just letters corresponding to those matrices above. And what I want to say is that this is not special to this 3 by 3 Vandermonde matrix. One of the amazing properties of totally positive matrices is that they have this so-called bidiagonal factorization. And the other feature of this bidiagonal factorization is that all of the factors or the parameters in those bidiagonals are all positive. I mean, there are zeros here elsewhere in the matrix, but you have this sort of property that all the pivots, if you will end up being positive as you present it in this fashion. So I just wanted to highlight that there, and I'll come back to this factorization later in the lecture. But it's just it's what ties the combinatorics in with the total positivity in general. Okay, so the first part of my lecture, I wanted to talk about this entry-wise preservers. And what I'll do is I'll generally speaking, I'm going to concentrate on preserving just powers of the matrix. So if you just operate the power function entry-wise on a matrix, then you just get this, you just get you just replace the matrix by the corresponding powers in each entry. And this is referred to as the alphth Hadamard power, where alpha is any real number you wish. And for the most part, I'll be considering alpha to be a positive real number here. It doesn't have to be necessarily integer, but positive real. Just because the matrix has positive entries, and I don't want to worry about other fields. So what you do is you start with a matrix, and now you just take the same power of each entry, and you just look at that matrix, and you're asking yourself, is there any kind of positivity that's preserved? And loosely speaking, or I guess the first sort of strata of questions you would ask is, is there a possibility that eventually these powers return back to the class of positive semi-definite matrices or totally positive matrices? And the answer is yes, this actually happens. And maybe this is a surprise, or maybe it isn't, depending on your background. And I think one of the most celebrated results along these lines is the Horn-Fitzgerald theorem from 1977, which states that if you start with a square doubly non-negative matrix, and just so I keep everyone on the same page, doubly non-negative means you're positive semi-definite and you're entry-wise non-negative, okay? So you have that double positivity, if you will. Then it turns out that the alphth Hadamard power of a doubly non-negative matrix is doubly non-negative, right? It'll be double non-negativity is preserved whenever alpha is a non-negative integer. Well, that's just Schur's theorem, but basically, or when alpha is a real number, at least n minus 2. So where this lower bound, of course, depends on the size. So integer powers work because Schur's theorem is there, and then it's the non-integer powers beyond n minus 2 also work. They preserve the property of being dn. This is a fairly incredible theorem, and for folks who study, entry-wise preservers, certainly with regard to the power function, really look at Horn-Fitzgerald as a sort of a seminal result. We can say something similar for totally positive matrices, but it's not nearly as pretty. So all we can say in some regard is that eventually there'll be some power, right? Some capital N, at least one, where for all powers alpha beyond n, you'll be back in the class TP. The problem is that we don't have a bound on capital N like we do here in terms of the size. So I'm not, we can't be sure that capital N is somehow fixed. It could grow rather large as little n grows. So it's not nearly as beautiful, if you will, as the Horn-Fitzgerald theorem, but it at least captures what I was sort of after. And that's just kind of the broad strokes sort of first steps in this regard. Looking more closely at entry-wise preservers. So here's just another way to view the alpha Hadamard power. And so I'm just going to use this notation here, F evaluated at a matrix. So you just evaluate the function entry-wise, and I'll sort of concentrate on the power function for the next little while, just as a matter of course. There are classical results in the context of positive semi-definite matrices, and I'm certainly not going to be able to go through all of them here or present them to you. I'll just take out a few that are somehow the sort of mainstays in this regard. So here's one where, if you have this series where the coefficients are non-negative and you know that the series is legitimate, it converges, then it preserves positive semi-definiteness, on some interval, but it's not really that big a deal. And roughly speaking, this is the way I've stated this is that it's not any really more difficult than just observing that the positive semi-definite matrices form a cone, except that you have to think a little bit about the infinite series, but it's still a beautiful theorem. And again, I didn't list all the people that have worked in this area, of course. For that, I apologize. But these are just some of when you read papers in this area, you will read papers of Schoenberg, Rudin, Polias, Ziago, Horn-Fitzgerald, and then others, maybe on the more total positivity side. And then the three that I've listed at the bottom, Dominika, Pruva, and Bala, maybe sort of north of 2010, the work that they accomplished while I think they were all at Stanford, and they've continued to work, really sort of turned the page on this area of enteric preservers. And they have a series of papers now, and they continue to produce papers where you really see a lot of different frameworks of this entry-wise preservers. And I don't have opportunity to say too much, except if you're interested, have a look at some of the works of these three gentlemen for more recent interest. One of the things that Bala and Apruva and Dominique did was they described this concept of a critical exponent, or at least they named it, I believe. And so the critical exponent is just the smallest power, or excuse me, the smallest number, so that you're preserved. You know, the alpha Hadamard power is preserved beyond this number mn. And so what you're really hunting for in the context of alpha Hadamard powers is you're hunting for this number m of n wherever, and then you get to choose your positivity class you wish, and you want to find this critical exponent, so this first place where every power afterwards stays in your class, right? And the good news is, of course, Horn-Fitzgerald did this. This is the Horn-Fitzgerald theorem I presented a few slides back, but I only gave you one side of the Horn-Fitzgerald theorem. Now I'm telling you the other side, is that not only did Horn-Fitzgerald say that beyond any power, any power beyond n-2 works, it preserves dn, they actually showed that no non-integer, for every non-integer power less than n-2, there is a dn matrix that's not preserved. So in fact, what they did show was they showed that the critical exponent for n by n doubly non-negative matrices is precisely n-2. So you have this sort of border right at n-2. Beyond n-2, everything is preserved. Less than n-2, if you're non-integer, you're not necessarily preserved. And if you have an opportunity to read this paper, I encourage you to do so, because they actually constructed a rank 2 doubly non-negative matrix that sort of is the sort of bad guy, if you will, and it turns out it happens to be CP. And in fact, we've been able to sort of see later on, it's actually totally non-negative. So there's the first theorem back in 77, where they sort of found this critical exponent in the context of dn. So then myself and Charlie Johnson, and others, we sort of switched gears from doubly non-negativity to total positivity. And we asked ourselves, is there any opportunity to sort of find critical exponents with regard to sort of restricting the case to totally positive matrices? So I'm losing symmetry, and I'm requiring that not just the principal minors being positive or non-negative. I want all the minors to be positive or non-negative. And here the results are not as pretty as the Horn-Fitzgerald theorem, but we do have results. So what I can say is that if you have a rectangular totally positive matrix, so here's an instance where I don't necessarily need it to be square. And let's just say you have at most 3 rows or 3 columns, however you want to think about it. Then the alpha Hadamard power is TP for any alpha more than 1. And in fact, you can argue that, or you can verify that 1 is actually the critical exponent in this case. So fractional power smaller than 1, or between 0 and 1, don't necessarily work. Okay, so there's a positive result. Oh, excuse me, that's a pun. There's an interesting result with regard to totally positive matrices, but I understand this is only when the matrix has 3 rows. So maybe that's not so interesting to folks, since it's not very general. So you say, okay, so let's do something more, right? And so let's look at 4x4 cases, 4x4 totally non-negative matrices or totally positive matrices. And I'm going to insert the word symmetric there. Now, your first thought might be, well, wait a second, are you just going back to the Horn-Fitzgerald thing? And it's like, not exactly, because I'm requiring all minors to be preserved, not just the principal ones. So this isn't exactly Horn-Fitzgerald. It's a little different. But what I want you to notice on the page is that we're returning a Horn-Fitzgerald kind of result. Namely, you get the critical exponent is again n-2. that same sort of lower, that same critical exponent that occurred in the Horn-Fitzgerald theorem. And so you might feel like, okay, wait a second, something's going on. And I imposed symmetry here. And of course, my size is still small. I mean, I understand that that's what's happening. Okay, so let's keep working, right? Like let's keep going. And myself, Charlie Johnson, and Alan Sokol were able to establish that there is no critical exponent basically after this case. So if you're sort of sitting around looking at n by n totally non-negative or totally positive matrices, then that bound grows forever. Like there is no fixed number where everything beyond will work and things below necessarily won't. And I'm not going to go through the proof of that. I can share the reference with you for those that are interested. But I will give you the sort of essence of the verification. And what we did here was we sort of looked at matrices of polynomials. And Alan Sokol has created a lot of work in the sort of concept of sort of coefficient-wise positivity. And so there you're asking about, you sort of separate these matrices out in terms of the coefficients regarding powers of x, and you want each of those matrix coefficients to be positive in some regard. And so that's what this coefficient-wise total non-negativity means. I mean, I'm not going to go through the definition, but it turns out that you can write down the determinant of the for this 4x4 guy, the determinant, the determinant of the Hadamard power of A in terms of alpha. And then from this little description here, you could argue that, boy, oh boy, you're kind of in trouble because of this difference here, right here. You're sort of stuck as long as x is pretty small based what's going on here. So you're not really, there's no chance of you keeping this determinant positive in some regard. Okay, so is that the end of the story? I mean, you have no critical exponent beyond 4x4 symmetric matrices? Well, okay. I mean, as mathematicians, we say to ourselves, okay, what if I actually impose symmetry in general? Well, it turns out it's not any better. The critical exponent is still infinity. And basically what you do is you just have to set things up so that it works. And the way I've partitioned this matrix here on the board is just to give you a sense that what we did was we take a 4x4 guy that we know is bad, and we kind of shove it in the upper right corner, and then we border in a way to sort of, work out that we make sure we got symmetry. Of course, we had to have a certain kind of symmetry in this 4x4 guy. You can't just do it arbitrarily, but I'm just giving you the essence of kind of how we approach this alpha's Hadamard power in the context of symmetric. Okay, so again, is this the end of the story? And I mean, roughly speaking, perhaps, but maybe asking for symmetry obviously wasn't enough. So what else can we do? And one of the things that seems to save us is the concept of Hankel. And if you understand what a Hankel matrix is, so these are the matrices that are constant along the anti-diagonal, right? So the entries depend on the sum of the indices I plus j. So if you require a matrix to be totally positive in Hankel, which, by the way, will necessarily be symmetric, then you get a Horn-Fitzgerald theorem back again. And so this isn't the Horn-Fitzgerald theorem. It's different, but it's, where it's like a cousin of the Horn-Fitzgerald theorem, I guess you can say. And the critical exponent comes back to be n-2, the same number that Horn-Fitzgerald noticed. And roughly speaking, the reason n-2 works is because you can use the tools in the Horn-Fitzgerald theorem to get the forward direction, and then the backward direction, we just go back to that the rank 2 matrix that Horn and Fitzgerald used, and we just have to adapt it a little bit to ensure that it's Hankel, and we can do that, or excuse me, we did that, and so you can just work it out. But honestly, that construction of the rank 2 guy is just based on the Horn-Fitzgerald theorem. We just had to work a little harder. There it is. I said that there. And again, the concept, it also turns out to be completely positive. But maybe that's for another time. The gentleman I mentioned earlier, oh boy, I'm going to forget who the Belton. Belton is the other person on this list. Excuse me. They've done a lot more than I have in this area, and so I've presented a few of their results here in the context of totally positive matrices. So if you're interested in other kinds of preservers, then basically only really the constant functions work. If you restrict dimension, then you can say a little bit more. Power functions come back, but there's not a whole lot there. Okay, now, whenever you have like a collection of positive things, it's very natural to put an order on those positive things and say one is bigger than the other. And of course, in the context of positive semi-definite matrices, you have the Loebner ordering, which is very natural. There are different kinds of orderings in the totally positive world. This is one of them. This is known as the tensor or compound ordering, and perhaps it has other names. But if you take two matrices of the same size, they don't have to be square, then I'll say that one is bigger than the other, if and only if the corresponding minors are ordered. And this is true across all minors, okay, of every size, as long as they're square. So these sets obviously have to be the same size. That's a typographical error on my part. I apologize. Don't fret too much about the notation. It's not that big a deal. I'm just saying that the corresponding minors are ordered in the obvious way. And I had a young man as a graduate student come visit me. He was from Bangalore. He came to visit. And so we started working on this problem here, where we wanted to find the functions that preserve the tensor ordering. The folks that I had mentioned earlier, Apruva, Dominique, and Bala, were working on entry-wise preservers that preserve the Loebner ordering, and they sort of called this Loebner monotone functions, and they did do lots of work there. So this is a bit different, but in the same flavor. Well, we did a little bit of work on this question, and then we sort of focused and specialized and so forth. And I just put out I put a question here that we were able to work out. And I respect the fact that it's just a 2x2 case and whatnot, but I just wanted to show you that, these questions are kind of tricky. So suppose I want to preserve these 2x2 matrices in this form, but I want to leave the 1-2 entry alone. I only want to operate on the other 3 entries. I mean, this is basically a game we all play. And it turns out that the functions that work are the functions that are sort of, they're non-negative on the non-negative numbers, and they satisfy this inequality, whatever that means for the function f. And so I just want to say that, even in the 2x2 case, you start, interesting functions start to pop out. I mean, even though I respect that this is sort of a basic case, but this did take us down a bit of a rabbit hole that I want to talk about now. So we got into combining the the tensor ordering with the Schur product, and we did all kinds of things. But this is the slide I want you to look at. And what we were doing was we were looking at this Toeplitz matrix H, and we were asking, we were trying to study this inequality H, the Schur product of H and A, and the tensor ordering, requiring it to still be totally non-negative. And it turned out, and I'm going to skip the details here because it's not interesting. It's just, working with your pad and pencil. It turns out that this inequality here regarding the determinant boils down to this determinantal inequality. Again, I'm skipping the details, but it's not complicated. This is, straightforward business. So, okay, so we wanted to check if this determinantal inequality happens to be true for totally positive matrices. And it turns out it is. Okay. But what this did was I realized that, geez, I need to get back and studying determinantal inequalities. Okay. And to do that, I need to talk to you a little bit about Lidstrom's lemma. I don't want to go through too much detail here, but you can read the slide as I say it out loud. So you have a network. It's an acyclic planar network, which just means it's a directed graph. You have sources on the left and you have sinks on the right, and you move from the left to the right. And it turns out you put weights on the edges, and as you move paths from a source to a sink, you multiply, you add up the weights of those paths, and that turns out to be so you take a path, you multiply the edge weights, and then for every possible path you add up those products, and that you produce numbers. And if you stack those numbers into a matrix, the matrix ends up being totally non-negative, and that's called Lidstrom's lemma. Okay, so I mean, I haven't gone through that. I'll get you a picture in a second. And in fact, Lidstrom did a little more. He didn't just say this works for the entries. In fact, you can write down formulas for the minors of this matrix. And so the minor of a matrix formed in this way, sitting in rows I, columns j, is just the sum of these products of edge weights in this planar network. And so what you might be interested in then is you say, okay, this seems interesting combinatorially, and it's particularly interesting if you happen to know these weights are actually positive, or non-negative, which turns out to be true in the totally non-negative world. So here is an example of a 5x5 planar network that we would be dealing with in this regard. So you have the sources here, you have the sinks here, and then you have this, you sort of travel along this diagram left to right, respecting the directions of the thing. And this represents, what I'm showing you here represents a 5x5 totally positive matrix. Even though I'm not going into all the details, I'm just saying that you can think of this as a 5x5 totally positive matrix. And so the inequality that I had presented a couple slides ago for 3x3 matrices was actually verified by Guntmacher and Krein in the 50s, maybe even earlier than the 50s. And that inequality turns out to be this one here in the middle of the slide, where the notation Aij is just, where you remove, it's a determinant where you remove row I and column j. Just that usual, coming from the cofactor expansion, if you will. And what you see here look like, A1j times the cofactor. So this looks like a sort of a partial Laplace expansion along row 1. And Guntmacher-Krein verified this, and one of these inequalities is the one I needed in that previous slide. Okay, so that's interesting. And I wanted to rewrite these inequalities in a different way. So you get this kind of, what this is saying is you get this kind of oscillation about the determinant as you add in more terms in the Laplace expansion along row 1. And so, okay, so that's just what it is. And in fact, it's this inequality here at the very bottom was the one I needed two slides ago. What we were able to accomplish is we were able to generalize the Guntmacher-Krein inequalities, using this sort of adjusted matrix here, and I've written them out here for you. I don't want you to. It's a bit of an alphabet soup. I don't want you to sort of worry too much about it, except I just want to point out that the inequality here on the bottom is the same as the Guntmacher-Krein inequality, except we're no longer required to go along row 1. We can go along any row or column we want, which sort of makes more sense. So we were able to extend that classical Guntmacher-Krein inequality. And the question might be is like, how are we able to do that? Well, we use planar networks to do it. Now, it turns out that Guntmacher-Krein inequality is actually a special case of a more general inequality. And again, please don't concern yourself with the alphabet soup here. It's just, these are just sort of typical kind of inequalities you might encounter in these sort of, particularly if you're interested in, say, Plücker identities and quadratic identities on minors, you'll see things like this a lot. And so what I was able to do with my postdoc pratique is that we were able to extend this idea of the Carlin and Muehlbach identities to get these determinantal inequalities that oscillate around 0, which further refines the original Guntmacher-Krein inequalities. So the point of the lecture, as I've tried to hint, is that we started with preservers. We looked at these weird kind of patterns of preservers. We were dropped into this world of determinantal inequalities. And then to verify these determinantal inequalities, we needed to dig into the combinatorics associated with totally positive matrices. And of course, I've spared you the details here. You can, I can give you the reference for the details, but these inequalities here that I'm writing down are all verified combinatorially. Okay, so they all depend on that planar network, and we verify these things by checking so-called subtraction-free expressions. And I'll just point out, okay, well, it's exactly lemma D in our paper, but of course, lemma D doesn't mean anything to you folks today. It doesn't matter, it's a lemma. And so what we were able to do is we were able to take an expression involving minors that we knew was non-negative, such as the Carland expression or the Gattmacher-Krein expression, and we developed these sequence of row operations, which I've just called R here, and you don't have to worry about it. And we were able to derive new expressions that are non-negative. So what we've done here is we have a different kind of preserver, right? We have a preserver of determinantal expressions, linear combinations of minors, and we are able to develop different linear combinations of minors, depending on this particular row operation. Again, at its very essence, this is purely combinatorial depending on those planar networks. Of course, excuse me, row operations, there's no reason to just fixate on rows. There's also a column version, of course, right? And then what you can do is you can intermix columns and row operations to really derive new kinds of expressions. And I don't want to go into all the bloody details, but there they are there. And of course, we have lots of questions about, can you go the other way around and so forth. And in certain cases, we have verified the converse, but certainly not in all the cases. But this has really opened a door into this sort of a whole concept of preservers and the mix between preservation and determinantal inequalities. This is just sort of saying some of the things that we did in that paper with my postdoc Pratik. And we established lots of different kinds of inequalities and adapted inequalities and expressions. If you are familiar with Plücker coordinates and the Plücker relations, or sometimes called the quadratic relations, there's a famous one known as the short Plücker relation, which involves 3 terms. That one appeared a lot. And then we moved to more, sort of different kinds of expressions of minors. If you've seen these so-called symmetrized Fisher inequalities, we dealt with that a bit, and we moved from there. So in conclusion, I think I'm nearing, well, I lost track of time, but hopefully I think I'm nearing the end. So what I did today, folks, is I presented a lot of projects. They spanned a lot of different opportunities and research directions. Many of my collaborators I've listed here: Michael Geckman at Notre Dame, Charlie Johnson at William & Mary, Alan Sokol at University College London, Saeed Mahmoud Manjagani, who's in Iran, and some of his students in Iran who helped me with some computations. And then my current postdoc, he's a PIMS postdoc here in Canada, Pratik Vishwakarma. I hope I said that right. Him and I in these last couple of years have really worked out a lot of these expressions, which I talked about at the end of my slide. Folks, I do apologize that I was not able to come to India, but I must really thank Prasad for giving me this opportunity to do it online. It's late here for me. It's approaching 11 o'clock p.m., but I do really, really appreciate the opportunity to give this lecture, and for you folks to taking the time in the morning there in India to listen to me talk over Zoom. I thank you, and I wish you all the best. Thanks.
So thank you, Professor Clark, for a nice talk. And so we have some time for questions and answers. We can take a few questions from the audience.
How does the total positive entries that contribute to the partial order structure of matrix?
Can you say that again? Sorry.
How does the total positive entry matrix that contribute to the partial order structure of a matrix? How is related partial order structure of a matrix? I think in your slide you mentioned that partial order structure, but it's related. Contribute to the partial order structure of a matrix.
Yeah. So So you're asking, how does it contribute to the,
partial order structure of a matrix?
yeah. So, okay, I hope I'm able to answer your question. So okay, so let me just make sure that we're talking about the same thing. So sorry for going through the slides. This one here, right?
Yes, yes, yes.
Yeah. So this tensor compound ordering, of course, you can choose the sets to be one by one, right? And so the entries of A have to be bigger than the entries of B. All the 2 by 2 minors have to be bigger than the other 2 by 2 minors. All the 3 by 3 have to be bigger. Is this the question you were asking?
Yeah, yes, yes. And
Yeah.
yeah. And that relation you define, that order structure, that can be partial order something. That means reflexive, antisymmetric, and transitive, all that property hold, or
I believe it is a partial order, yes. Yeah. I don't think it's I have to be careful here. Yeah, like I'm not sure it's transitive. I don't believe it is. But reflexive, sure. Yeah. Symmetric, yeah. I believe it is a partial order if I've answered your question, but it's not a very nice order, that's for sure. Sorry, I mean, maybe I'm not answering your question very well, sir.
Okay, so any other questions?
Yes, the theorem you mentioned of Fitzgerald.
Yes.
This is counting the paths. You take the product of the weights along the path. That can you
Lindstrom.
yeah. The other name I am forgetting probably.
Lidstrom. Oh, sorry. Pardon me.
Yeah.
I don't remember where it was now. Oh, this one.
Yeah. No, the picture,
Yes.
you had a picture also. A graph.
Yes.
This is one. Yeah.
Okay.
So what you are saying is you are taking the product of the weights along the path.
Right.
I don't get the matrix.
Right. So, okay. So let's say you want to calculate the entry
Say 2, 5.
2, 5.
Yes.
So you follow a path across,
Yes.
and then you go all the way up to 5, right?
Yes.
I haven't put the edge weights here, but you multiply all the edge weights. But there's more than one way to do it, right? You can go all the way across and then up.
Yes.
And so you add the products of those paths and you'll get the 2, 5 entry.
Okay. And then this statement is that matrix is totally positive.
When all the edge weights are positive. Yes, sir.
Yes. So
Yes.
Carlin had a similar theorem with his co-author in the probability area.
Yeah, Carlin McGregor.
Yeah, Carl McGregor.
Yeah.
And whose was the first one? Was it Carlin or?
Okay, this is a great. I believe Carlin McGregor were first. Yeah, but in that paper that Carlin McGregor worked, they were working with what's called birth and death processes.
Yeah,
and so they were working with a sort of it was almost like a tri-diagonal matrix, right?
yeah.
So it wasn't a completely general, totally positive matrix. So they definitely had the first result using these products of weights of paths, but Lidstrom verified it sort of in complete generality. But he was 20 years after Carlin McGregor.
And also in the case of Carlin McGregor, they were trying to manipulate permute something to do with the permutation of the paths or something like that. I mean, it is the determinantal. I'm vaguely remembering it. 30 years back.
But you're right. So what they showed was that if those paths intersect, then basically that minor gets canceled out, or excuse me, that term gets canceled out. And so you only care about the disjoint paths. Yeah.
Disjoint paths.
Yes, sir. Yes, sir. Yeah.
Thank you.
Yeah, of course. Okay. No, thank you.
Okay, so let's thank Professor Sanfala for his wonderful presentation.
Thank you. I appreciate it.
So our next talk will be an invited talk. Maybe get another. We can wait for another 1 or 2 minutes. We can wait for another 1 or 2 minutes. Thank you, Professor Sanfala.
Thank you.
Almost.
So our next speaker is Michael Matila, Denver University Lab. So it's the offline talk, and the title of the talk is applying a lattice theoretic method in the study of power LCM matrices. Over to you, Professor Mike.
Yes, so thank you very much. And first of all, just like Professor Fala just thank the organizers of this conference, I would like to do the same. So I would like to express my own gratitude to all the organizers, and especially Professor Manjunath Prasad, who has helped me significantly. And as some of you know, I had some difficulties with my flight, so it wasn't very easy to get here because my flight was delayed quite a lot. But thanks to our local organization team, I was able to conquer those difficulties. All right, so I'm here to talk about these power LCM matrices, and many times people want to ask me what is this research related to, and what are the fields of mathematics that you need to understand if you want to study these matrices. And of course, you need some linear algebra, you need some maybe lattice theory, a little bit at least, and maybe some knowledge about number theory as well. And but if you really want to understand this method that we are using here, you actually need to understand some combinatorics as well. And I think this becomes soon quite obvious, but I'm not going to go through all the details, so I try to just give you some general outline how this thing works. And I have been studying quite a lot of, and our team has been studying these usual LCM matrices, but it turns out that our methods actually work quite well with these so-called power LCM matrices as well. But you have to just apply them slightly differently. All right, so seems that my pointer. So changing the slides is a bit difficult. Okay, now great. All right, so first of all, I should give you a proper definition of GCD LCM matrices. And so first of all, how do you construct this kind of matrix? Well, first of all, you need this finite set of integers, positive integers, and also we assume that they are organized this kind of in this increasing order, and we don't allow any repetition in our set obviously. And so this is the first thing. And next thing that we later assume is that we want our set to be GCD closed. Of course, you don't have to assume this. You can form your LCM GCD matrices without without assuming this, but we actually like to study these matrices under this condition that this set is GCD closed, because it makes certain things a little bit easier, and that's a positive thing for us. And then, because we want to study these power matrices, we also introduce this real number alpha, which will be the exponent in this story. And now we can actually construct these matrices just like it's shown here. So in the GCD matrix, the AJ element is the alpha power of the greatest common divisor of xi and xj. So it's quite obvious from this definition that this matrix is symmetric. So if you interchange the roles of xi and xj, the values remains the same. So that's very easy to see. And another remark is that if you forget the exponent, then you get the usual GCD matrix, and so basically in that case alpha equals 1. So this general GCD power GCD matrix is just the alpha Hadamard power of the usual matrix. So Professor Pala very nicely introduced the Hadamard powers, so you should be pretty familiar with those at this point. And actually, another interesting remark is that these GCD matrices have been shown to be totally positive in the sense that Professor Pala just told you in his talk. So these matrices are quite well known at this point. But on the other hand, these LCM matrices, they are a totally different story. So they actually don't have any nice positive definite properties, and they can even be sometimes singular. And so in some sense, there is quite a lot of more to do with these matrices than with the GCD matrices, and that is one of the reasons why we are today talking about these LCM matrices. And the definition for LCM matrices is pretty much the same. You just use the least common multiple in the place of greatest common divisor, but in the end you just use the alpha exactly the same way. So we can change slides once again. This can you do something? Or is this off? All right, so great, thanks. So there was a trivial solution to my problem. All right. So in this GCD and LCM matrices were actually introduced quite a long time ago. It happened something like 1879 was, I think, the year when this British mathematician H.G.S. Smith introduced this matrix type. And over the years, they have been studied, not very extensively, but in the 1980s, this kind of new research group started considering this type of matrices, and they actually ended up conjecturing this conjecture that I have shown you here. So they wanted to find out conditions under which the LCM matrix is invertible, and they couldn't find a counterexample to this, so they conjectured that assuming the set S to be GCD closed actually guarantees the invertibility of the LCM matrix. But later it was shown that that is actually not the case. So there is a 8x8 counterexample, and which turned out to be minimal. So that's but that took something like 5 years before the first counterexamples were found. So the conjecture actually holds for matrices of size 7x7 and smaller, but for the 8x8 case, there is you can find counterexamples. And so we actually have studied the usual LCM matrices by using our lattice theoretic method, and we have also studied the 9 element case where and characterized all the semi-lattice structures that can be used to produce this kind of singular LCM matrix. But I'm not going to do that here now, because now I would like to focus on these power matrices. So here are two important questions that I would like to answer today. So first of all, what conditions would guarantee the power LCM matrix to be non-singular for all exponents alpha? So that's obviously these conditions must be quite restricting, because even in the usual case, the GCD closeness was not enough. And now we actually allow even more, infinitely many more cases, because of this alpha can be whatever positive exponent. And on the other hand, is there some kind of limit? If you can you find singular power LCM matrices with arbitrary large exponent alpha? So that's another interesting question, and also that I would like to be able to answer today. So here is the actual matrix theoretic part of my talk. So first of all, we would like to be able to study the singularity by using the determinant. So how do we do that? Well, first of all, we start with factorizing this power LCM matrix by doing this kind of factorization. So we in some sense we write that matrix in terms of this so-called reciprocal power LCM GCD matrix, just by putting those two diagonal matrices on left and on the right hand side. But this is not just enough, because we still have to factorize this GCD matrix a little bit further. So that for that we have certain very famous theorems known from the 1990s. But nevertheless, I'm not going to show you the details, but this matrix in the middle can be factorized, and it can be done in such a way that we have at the end we have a diagonal matrix in the middle, and triangular 0, 1 matrices on the left and on the right, and where all the diagonal elements are equal to 1. So basically, the determinant of this power LCM matrix is actually just the product of the diagonal elements of the diagonal matrix in the middle, and so the determinant looks like that, and that is actually the reason why we like to assume the GCD closeness of the set, because if you don't assume that, then you cannot have this kind of nice determinant formula. And but once you get this formula, it is now obvious that this determinant is non-zero only if and only if every one of these psi values is non-zero. So that is now the question: what guarantees all of these psi values to be non-zero? Okay, so now we need some combinatorics, and here was the definition for the psi value. So you actually need the Möbius function of the corresponding partially ordered set, or it's actually now a semi-lattice, because we assume the GCD closeness. So that's another thing to keep in mind. So we of course don't want to miss any non-negative terms, non-zero terms. So if this Möbius function value becomes 0, of course we don't have to care about that kind of term at all. So this lemma was actually needed to guarantee that we can focus on certain elements in the lattice, and among those elements are all of those elements whose Möbius function value is non-zero. And so basically what this means is that for element x, if we consider all the elements that are covered by x in this semi-lattice, and then they take the greatest common lower bound of those elements, then and consider that interval, then that interval actually contains all those elements that have non-zero Möbius function value. Or to put it in the other way, all the elements that are outside this interval will actually have their Möbius function value equal to 0. So we had found out that this we need this kind of result, and we proved it by using just elementary methods. But actually, you need this kind of double induction. So first on the size of the elements covered by this X element, and then also on the size of the interval. But actually later, when that article was already published, I was plowing through the Martin Eichner's famous book Combinatorial Theory, and I found out that this result actually follows from one of those theorems there. So it actually wouldn't have been necessary to prove this in the article, but what that we did, and even the referee didn't, although he had some other clever comments, he didn't have any clever comments about this one. So this proof is actually in the final article. So let's give some examples to illustrate things. So if you have a chain, then what happens here is that you actually this is so-called positive situation. So whatever this exponent is, you can calculate these psi values, and whatever the exponent may be, all these psi values are non-zero. So this is maybe one of the most simple cases that you can have, but at least in this case we have a definitive answer. So let's consider a bit different case. So now I'm studying this kind of 4-element structure, and one way of following it would be to consider the numbers 1, 3, 5, and 45. And now if we calculate all those psi values, we can see that the first 3 are obviously always non-zero if alpha is positive, but the last one actually takes both negative and positive values depending on close to 0. We are actually on the positive side, I think, yeah, and then we have become negative at some point. But that's not important. The important thing is that it takes the value 0 at some point between 0 and 1. So here we have an example of a very simple situation where one of the Hadamard powers becomes singular. But if we just modify this example a little bit, we replace the number 45 by 15, then that actually shows that also this last psi value cannot be equal to 0. So in some of these situations, it's actually, although also those elements of the set S actually play some role in this. But if these elements are chosen in a proper way, then we can obtain a singular matrix which corresponds to this set. So now we get to our main theorem basically. So there is some explanation, but what this theorem actually says is that if we have a situation where some element covers several, at least 2 elements, and the Möbius function value of the top element X and the element Y, which is now the meat of all those elements covered by X, then if this Möbius function value is positive, strictly positive, then in that case it is possible to form this kind of set of positive integers, which is isomorphic to this semi-Lie structure, and then there is also this kind of exponent alpha 0 for which the power LCM matrix becomes singular. So these conditions seem a bit strange, but yeah, if this kind of situation happens, then we can always get a singular matrix for some exponent. And of course, in this case, we had this element covering 2 elements, and the Möbius function value between this one and this one is equal to +1. So that is actually the explanation why that example works. So probably it's better not to go through all the details of the proof. I will just give you some general idea what happens here. So first of all, we begin by constructing this set S. So we of course need to introduce some prime numbers, and we just take a note from the actual semi-lattice structure and define these elements. Let first element to be equal to 1, and then the other elements are then defined as products of those prime numbers by using this idea. So if you do this way, then you get a semi-lattice which is isomorphic to the one that was given to us in the beginning. And then there is also this one problem we still have, and that's the problem that if you do it this way, then this top element, which is now denoted by xi, may be too small. So we may have to make that element a bit bigger, and so that's why what happens here. So if we make this xi bigger, and of course we need to make all the elements that are above xi bigger as well. So that's why we need to apply this kind of trick. So we multiply every element which is divisible by xi by this prime power pi to the power r. And of course, this trick does not affect on the structure of the set. And now we just form this psi value, and of course we have fixed the structure of the set S. So the alpha is the only variable in this story here. So this is basically a function of one variable. Alpha is the variable, but this function is simply the psi function value of the element xi, and this we would like to show that this actually now becomes 0 for some value of alpha, and that really happens because we just have to modify this expression a little bit. So we first of all we take the first term apart from the other terms, and take this 1 over xk to the power alpha as a common factor. It of course it divides everything else in the sum, so we can pretty much do that. And now we start thinking about what this function now does on the between 0 and infinity. And first of all, it is quite easy to calculate the limit when alpha goes towards infinity. So because we have something in the denominator in all of these terms, if alpha really goes towards infinity, then the denominator increases infinitely, and basically that whole sum will go to 0. So the only thing that is left from this is the first one, the Möbius function value, and of course we assume this to be positive right in the beginning. So this at the infinity we go towards some positive integer. And actually I forgot to say that we took this common factor because it doesn't really affect on this term to be 0 or not. So that's why we are not considering this function itself, but here we actually consider xk to the power alpha times the function, because we are only interested in the zeros at this point. But all right, so this goes to some positive integer in the infinity. So what does it do around 0? So that is actually very easy to evaluate this function at 0. So we just put 0 in its place, and the definition of the Möbius function guarantees that this actually takes the value 0 at 0. So it takes the value 0 at 0, but and it goes towards some positive integer at the infinity. So what does it do in the middle? And that's a great question. We would like it to take some negative values in the interval. So how do we know that it takes some negative values? Well, we can of course use the derivative. So that's the very elementary approach. If you can show that this function has negative derivative at origin, then of course it will have to take negative values right on the right hand side of the origin, and then we can basically apply Bolzano's theorem. And so we just need to derive this with respect to alpha, and that's a bit complicated, but not terribly complicated. But what we get is after arranging some terms, we can put it like into this form. And now earlier we did this trick, so we increased these certain elements and put that power r there. So in this at this time this r really comes to play, because it appears over there, and if this term is sufficiently large, we can basically make sure that this well, of course we first need to take the value of the derivative as 0, so that's the first thing to do. But then once we get that out of the way, then we ended up with this kind of expression. And now if we this r happens to be large enough, then we can see that all these this term will have to be able to cancel all these other terms, whatever they may be, because they don't include any r's there. So it is possible to find sufficiently large r such that this becomes negative. And at this point, we now know that this function takes negative values right on the right side of the origin, and at some point it goes towards some positive integer. So there has to be value 0 at some point in the middle, and that's basically the end of that proof. All right, so then we have this next theorem, which is actually a consequence of the previous one. So maybe this proof is much more combinatoric, so maybe it's better idea to skip that. But basically, you can characterize the theory of the property of the semi-lattice. So it has to be a tree if you consider that as a graph. So there has been many talks about graphs and matrices, especially yesterday. But here we actually have a connection between matrix and graph, but in a very different way. But still, it's quite funny that actually this if the diagram of the partial ordering appears to be a tree as a graph, then that is actually what we need if we want this power LCM matrix to be non-singular for all exponents. And yeah, so the proofs are a bit tedious, but the details at least. But nevertheless, you can basically the first implication is actually the most difficult. The other ones are quite straightforward. So I'm not going to say anything more about that. But I would like to conclude this talk with this last conjecture. So there was this in 2002, this Chinese guy Fong gave this conjecture that in which he conjectured that this power for every positive integer it is possible to construct a GCD closed set for which the corresponding power LCM matrix is non-singular. So this is his conjecture formed exactly as it was appeared in this paper. So we would like to consider this, but of course we cannot do with integers. We have to allow the exponent to be a real number, because otherwise our methods won't work in that kind of situation. So we managed to prove just recently that actually if you allow the exponent to be real number, then there is no any kind of limit where you can find a power LCM matrix with that is singular for however large exponent. So you can basically go beyond any border there. And so here, but what you actually need to do is you need to just add enough elements to your sub-semi lattice or whatever. So this k actually is the number of elements that we need to introduce to make this exponent become large. And this k has to be so large that logarithm of k divided by logarithm of 2 is greater than or equal to m, where m is the bound that we want to exceed. And then we consider this kind of set of positive integers, 1, 2, 3, 5, 6, 10, 15, and then we have group of prime number elements where they are all multiplied by 2, and then we have 30 times the product of all these primes. And so it will look like this. So this is the so-called cube, where we have these side elements and quite a lot of them, actually. And the Möbius function values from the top element to each element has been put here. So the interesting thing is that the Möbius function value of this element equals k, and k can be now be very large. And so we'd like to show that this has this corresponding LCM matrix is singular for some value larger than m, basically. And now we just calculate the psi function value of xn, which is the largest element of the group, and we just reorganize those terms, and then we are basically put these into three categories, actually 4. So this is non-negative for all alpha greater than or equal to logarithm of k divided by ln2. This is non-negative for all alpha which are at least 1, and this term is also non-negative provided that these prime numbers are large enough. So we cannot specify at the beginning what are those prime numbers, but here we need to check that they are large enough so that we can put this term to the positive side. And then of course we have this one more additive term which is positive. Okay, this is actually my last slide. So again we do the same trick as previously. So we notice that this at the infinity this goes towards -1, but between 1 and this number here, this function is positive. So there has to be a 0 right after this value here. Again by Bolzano's theorem, which was first proved in 1870. So yeah, that's the end. So thank you very much for your attention.
So I thank Dr. Mahinda Metila for his very interesting talk. He is one such speaker who is working in the intersection of number theory, linear algebra, graph theory, special matrices. So he's covering all the topics. And he's working on a conjecture, that project, lattice theoretic study of the Work-alike conjecture. And what is the status of this conjecture? I mean, is there something to do more?
Yeah, there are actually many open questions. So this conjecture remains open still. So we have studied it experimentally in the second power case, and even that seems to be quite difficult. So we haven't managed to find this kind of verifying sample. So yeah, there are many open questions.
So I guess that some of the participants might be interested to work on this topic. Is there anybody who is working in number theory? So any questions? So in any case, that this will motivate our participants to work in the intersection of different areas. And
this topic goes well with the special matrices.
Yes, this topic that I can see that the special matrices are included in your revision. And is very appropriate talk and this kind of that. The speaker, in fact, the speakers covering all the areas. And so if there are no questions from the participants, then we can have a tea break. And let's thank the speaker once again.
On behalf of CAREMS, I request Professor Niyogi to honor Professor Mika Martin.
Yeah. Maybe.
Thank you.
I think we have missed the previous speaker also to give the phone.
No, I'll keep it.
Okay, okay.
I didn't tell him that.
Thank you, professors. We shall now have a tea break and contributory talks will start at 11 o'clock in academic block 3. So contributory talk A will be held at room number 403. Contributory talk B will be held at NLS 404. Contributory talk C will be held at NLS 405 and contributory talk D will be held at NLS 303. Thank you. Following which afternoon session will start at 2:30 in the same hall. Thank you.
Who is having the key for that room? Sorry, she is there? Or is it Danya? Alex. He was here. Huh? I saw her. Anybody going there? Yeah, maybe just after the tea break. So. Thank you.